Hi, today we're going to be talking about how we run Apache Airflow at scale at Shopify.
So my name is Jean-Martin Archer. I'm a staff data engineer at Shopify, working with Michael in the Data Foundation compute team.
And I'm Michael, and I'm a data engineer at Shopify, also on the Data Foundation's compute team. Our team maintains the compute primitives that data scientists and data analysts use to be impactful, specifically query engine and orchestration. Both JM and I focus on developing and maintaining our custom Airflow infrastructure and integrations and work closely with the data reliability team. Today, we'll be talking about how we use and deploy Airflow at Shopify, some challenges we've encountered running Airflow at scale, our new, more scalable multi-instance Airflow architecture, some of our custom Airflow developer tooling, and what's ahead for our team. So before we get into exactly how we use Airflow, we should probably provide an overview of what Airflow is to give those who are unfamiliar with the platform some context. Apache Airflow is an open source workflow management platform to programmatically author, schedule, and monitor workflows. Airflow uses DAGs, which stands for Directed Acyclic Graphs, to orchestrate the order and flow of tasks in a workflow. DAGs are defined in Python scripts, taking on a configuration as code approach. Each DAG is defined along with a set of extensible and configurable operators that allow for easy integration with GCP, AWS, Kubernetes, and more. One especially useful feature that arises from DAG files is the ability to dynamically generate DAGs. Using a for loop or a config file, many DAGs can be defined in one file. Airflow also has a user-friendly web client to interact with DAGs and view DAG runs. At Shopify, we have over 12,000 DAGs in production and over 400,000 task instances running daily. While these numbers sound daunting, a lot of our DAGs are dynamically generated by data platform tools and abstractions built on top of Airflow. Our Airflow infrastructure supports over 600 data scientists and many core and data platform internal customers, all supported by JM and me with some help from the data reliability team. Airflow is a foundational component of our data orchestration platform. There are essentially three types of DAGs that we have at Shopify. The first is config-based workflows that dynamically generate DAGs from config files or some data platform abstraction. Some example of these include our batch data ingestion systems that ingest data from APIs and streams, as well as our Trino and BigQuery-powered dbt modeling platform. The next type of DAG is user-generated, but takes advantage of complex frameworks built into custom operators, like the ML model training pipelines that we use for custom ray operators. Finally, we have ad hoc jobs that individual data scientists that will need to schedule. Airflow was introduced into Shopify's data platform back in 2019 when orchestration heavily relied on Uzi and Azkaban. In order to best meet the needs of data scientists, the platform shifted towards a centralized Airflow environment in 2020. Then in 2021, we upgraded to Airflow 2 for huge performance improvements, and after migration to Airflow was fully complete. This past year, through Shopify's data platform growth and scale, we've pushed the limits of what can be run in a single Airflow instance and introduced a multi-instance architecture, improved our tooling, and established better reliability practices. The core components of Airflow are a set of web servers, schedulers, and workers. The web servers run Airflow's web client and API. The schedulers handle DAG file processing and task scheduling, and the workers execute tasks. At Shopify, we run our own in-house Airflow infrastructure on GCP using Cloud SQL for a managed MySQL database, a mounted file store, and GCS for deploying and storing DAGs. For each instance of Airflow, we deploy Airflow's native components, Redis as a message broker, and a set of Cloud SQL proxies to connect with Cloud SQL. A unique feature of our infrastructure is the way we combine GCS and file store to achieve low latency DAG deployments. There are two typical approaches to deploy DAGs in Airflow. The first is storing DAGs in GCS and accessing GCS from the Airflow components, but introduces latency issues that comes from network call limitations. This is what Cloud Composer does. The other standard approach is baking DAGs directly into the Airflow image, but this creates a slow iteration speed since each time you want to make a change to a DAG, you have to build a new image and redeploy your Airflow instance. We take a hybrid approach, allowing DAGs to live in GCS, syncing the DAG bucket with a mounted file store using a custom syncing daemon. This allows for the fast iteration speed of using GCS and reduced DAG update latency. Now that we've gone over how we use Airflow at Shopify, let's talk about some of the challenges we've come across running the platform at scale and how we've overcome these challenges. So a huge challenge of running a system like Airflow with hundreds of internal users is managing DAG ownership, task resources, and ensuring DAG developers comply with best practices. When you have tens of thousands of DAGs in production that are owned by various teams, it can be pretty easy to lose track of who owns what workflow. When a DAG that services stakeholders that depend on it works reliably in the background, it can be easy to forget about who owns it. When it breaks and you don't know who's responsible, it can be costly. In order to maintain a clear structure of ownership of DAGs, we have the concept of Airflow projects, which is a collection of workflows with a defined owner, source repository, and dedicated K8 namespace, along with shared resources and secrets. To help with troubleshooting DAG deployments, to help troubleshooting with DAG issues, we append a header to the top of each DAG file on deployment with its GCS path, local path, Git repo, and commit information. We also ensure DAGs meet our best practices by applying a set of custom DAG validators and mutators. This is a cool customization because we're not validating or mutating the script, but rather the parsed DAG objects. For example, we check that a DAG has a valid schedule and ensure that the DAG is part of an existing Airflow project. We also apply a set of DAG mutators to properly tag DAGs so that we can filter them by project, and in the future plan to edit task resources to set limits. Another significant challenge of running Airflow at scale is dealing with dependency conflicts. When you have a wide variety of teams using the same Airflow environment, installing new dependencies and resolving conflicts can be a nightmare. This can be especially difficult pain point when upgrading Airflow versions. A great solution that has become an industry standard is making use of the Kubernetes pod operator. This operator allows you to execute your task in a dedicated Kubernetes pod with a pre-built image that you provide. You can install whatever dependencies you want into the image and run your task and don't have to worry about conflicts. So we encourage dependency or resource-intensive workflows to take advantage of these operators. This also makes our Airflow image lighter weight since most of the packages we need to install are for custom operators and integrations. The biggest challenge we faced running Airflow at scale is the scheduler performance issues. The Airflow scheduler does two things primarily: DAG processing and task scheduling. The DAG processor parses DAG files and updates the database with DAGs and changes to existing DAGs. The scheduling process starts new DAG runs, queues associated tasks, and assigns them to workers for execution. We found that the scheduler can be a key bottleneck for task scheduling latency, which can cause DAGs to be executed late, and DAG parsing latency, which causes a poor user experience. To avoid DAG processing performance issues, we encourage DAG developers to avoid network calls and CPU-intensive code in the global scope of DAG files because Airflow scheduler will parse that DAG file. A primary issue with DAG processing latency is the effect on developer iteration speed, so we also have a custom API endpoint that downloads and processes a DAG file so that the developer doesn't need to wait for the DAG processor to parse their file if it's running slow. We found that the largest cause of task performance issues at scale is metadata related. When you execute 400,000 tasks per day, it's pretty easy to rack up tens of millions of rows in Airflow's database. Not to mention the fact that the scheduler executes complex joins, filtering, and ordering in order to find and prioritize the right tasks to be executed. To mitigate these metadata-related issues, we aggressively truncate our Airflow tables, keeping 1 to 4 weeks of DAG run and task instance history. We also make good use of Airflow pools and priority weights to make sure critical workflows continue to run through slowdowns. We use MySQL since it's the main database management system at Shopify, but the Airflow community prefers Postgres and it's better supported. This combined with our scale leaves us finding interesting bugs like missing indexes or the query planner using the wrong index, so we frequently find ourselves contributing upstream fixes for MySQL. While we've been able to manage vertically scaling a single Airflow instance with some of these mitigation strategies, these metadata-related challenges tie into the need to horizontally scale.
So that leads us to us running using multiple instances or adopting the multi-instance Airflow architecture, or in other words, sharding or cluster. So next slide. Michael, the next slide. Oh, thank you. So why horizontally scaling? As mentioned earlier, vertically scaling got us pretty far. If we think about the number of DAGs we got, we actually reached 400,000 tasks per day with 12,000 DAGs. And the joke is that when we tell the Airflow maintainers about our scale, for them a stress test is about 1,000 DAGs. So we clearly reached the limit of what should be reasonable in a single instance. And also at the same time, in the near future, we're about to double or triple the number of DAGs we have. So regardless of whether we want it or not, like we needed to start sharding our instances. And one of the major issues we had, like as mentioned with the list of issues we encountered with Airflow, the blast radius was just massive, which meant that any performance issue, an incident, even plan upgrade, would introduce a significant outage or a significant downtime to all the possible DAGs. And some of those DAGs are quite critical. For example, all our data ingestion pipeline, as discussed, is going through Airflow. And those can be quite critical because some of the Kafka topics that some DAGs are consuming have a very short retention period. So sometimes we got up to 12 hours to get the issue fixed. And as mentioned, one of the issue is that also as far as having a support tier for our data reliability team, if there was an incident, even if the DAG, a lot of DAGs, it's not a big issue if they're down, but those data ingestion DAGs are quite critical. So we needed to give them a clear boundaries where they can, when that team knows when to, if an issue needs to be jumped on immediately overnight, or can it wait the next day for us to look at it. So in this diagram, it's no surprise. Basically, we just end up with two, well, more than two, but quite a few different distinct Airflow instances. And one of the key things is that right now we are sharing the same resources. So we're still sharing the same database server. If we go to the next slide. But they are running on their own instance, their own Kubernetes namespaces and whatnot. We have the ability to dedicate specific database server to different instances if needed, but at this point we have not seen the need because we were the existing database and other infrastructure was doing okay enough with a single massive instance, so it's keeping up finely or just fine with the multiple instances, but less DAGs or the same total amount of DAGs, I should say. So as mentioned, we're using the same JE cluster, database server, GCS bucket, and NFS server. And one of the perks of doing that is that to create a new instance, there's no infrastructure change to be done on our end. So effectively, we create, or our clients could create a new little JSON blob on the top corner over there. And that will render all the Kubernetes manifests required, and it will configure everything perfectly. And at deployment time, everything will be provisioned, so within 5 minutes. And on top of that, we had to make sure that all our metrics are pre-tagged, scope by environment, instance, tier, namespaces, and cluster. Therefore, us and the DRE team could be able to clearly see which instance or which environment is having some issues. And a key factor or an important thing is that also any configuration of Airflow itself is also managed in the same deployment pipeline, which means that connections, user role mapping, pools are all stored in Git and can be applied consistently across all the instances. So it's frowned upon to go in the Airflow UI or even the command line tool to change stuff manually. So next slide. One of the challenge we had, or something we really care about, was the concept of DAG routing, which effectively would give us the ability to move DAGs to different instances transparently of the users. So as discussed, right now, all the teams write their DAGs to a shared DAG repo, not repo, but the GCS bucket, like an S3 bucket. But we did not want them to have to worry about like modifying their deployment script so their DAG gets deployed to a specific instance. So instead, the approach that we went is that we modified our GCS NFS sync daemon to read from the project definition file that Michael mentioned earlier, where we'd specify the instance name, and then the structure, the daemon will create a specific structure for the DAGs of that specific instance. So on the second image, you can see that for the general instance, it has a set of DAGs that the instance itself can see. where the other instances could not see them. Effectively, Airflow doesn't know any better. It will just load those DAGs because that's what it can see. One of the main caveat with that approach is that when we migrate DAGs around between instances, right now we do not preserve the history or the metadata. And also, depending on how the DAG is written, the DAG may just execute instantly as soon as the new instance sees the DAG. And another caveat with that is that since the DAG processors and the two instances are working independently, some DAGs may still be running in the initial instance, and they could start running instantly on the new instance. So depending on if there needs to be guarantees about like only one running at once, we would need to delete, make sure that all the DAGs have been removed from the old instance, make sure that all the tasks have drained, and then add it to the new instance. So there could be a gap where there's no DAGs. Next slide. So then where the question comes, if we made it so transparent for a user, they don't have to worry about the DAGs, then it could get quite confusing about where are my DAGs? So how we resolve that, it's since Flask is since Airflow is fundamentally just a Flask app, quote unquote just, it means that it's extremely extensible. So we were able to add the concept of projects to the Airflow UI and also the API. So for users, if they're looking for their project exactly, like if we look at the second picture, they just have to click and they'll be instantly redirected to the right instance. And same thing, we added some extra observability links for us and the DR team, where, for example, if we click on the link highlighted in red, it will link us to a dashboard that is exactly filtered for the instance and for the database and for the namespace and all that stuff. So effectively making sure that the operators are not overwhelmed with irrelevant data. On the API endpoint, since we're using Airflow programmatically across like multiple services and whatnot, we also added the same concept as far as being able to list instances and mapping projects to instances. And that's a segue into Michael's.
So we've developed some custom tooling to make interacting with Airflow easier. Surf is a CLI and Python library for interacting with our remote Airflow environments. It integrates with both Minerva, Shopify's browser-based OAuth authentication flow, and Basic Auth for service integration. The main value of Surf for DAG development is the ability to iterate quickly with an environment close to production in terms of resources and security. With Surf, each user can upload DAGs directly to the staging environment with instant DAG parsing and loading. They can also trigger, list, and monitor DAGs, as well as bulk, pause, resume, or fail DAGs. Surf can also list, update, and upload connections to our staging environment. Surf makes interacting with the Airflow API easy, but also abstracts away the multi-instance architecture that Jan talked about. The challenge with having multiple instances within an environment is that the URL that you want to send an API request to depends on which instance your DAG is deployed to. Based on the environment and project you want to interact with, Surf routes its API request to the right instance. Using the Surf CLI, users first set their environment and project using the Surf mset and Surf project set commands. Alternatively, the environment and project can be passed in through environment and project flags in other commands. Users can list all DAGs matching a specific DAG ID pattern with the Surf DAGs list command, and pause or resume DAGs by running the Surf DAGs pause or Surf DAGs resume commands. You can trigger a new DAG run with the Surf DAGs trigger command and fail the most recent DAG run of a DAG with Surf DAGs fail. The most useful command is probably the Surf staging DAGs push command, which uploads the specified file to the staging environment and processes any DAGs within that DAG file. So to go over a quick example, let's say I've been working on this DAG in preparation for PyData Global, and I want to test it in staging and make sure it works. I run the Surf staging DAGs push command, passing in the environment, project, and the path file. And within a few seconds, my DAG is uploaded into GCS, parsed in Airflow, and I'm provided with a link to my DAG, which immediately shows up in the Airflow web client. Also, if my DAG had any import errors, they would be displayed to me in my terminal instead of having me to go to the Airflow UI. The greatest benefit of Surf is the quick iteration speed, while interacting with a real Airflow environment instead of having to support a local development alternative.
So what's ahead? So if we go to the next slide. Michael, next slide. So we're in the process of grading to Airflow 2.4. So we're about there. If it wasn't for this presentation, that's what we would be doing right now. So it's already tested and staging and everything. We just need to deploy it to our production environments. Something we look forward to is give our users proper support for data-aware scheduling that was introduced with Airflow 2.4. And one of the challenges for us is that we have to make it work across instances, because we can imagine, it's easy to imagine that a DAG may want to be triggered after a certain part of the data ingestion part. DAGs have been processed, and those two logics or those DAGs are living in different instances, so they don't know necessarily about each other. So we'll need to make that work. We do want to adopt open lineage, which was introduced, I think, in Airflow 2.3 or maybe 2.4. And for effectively giving, there again, doing the lineage and data origin of data and whatnot. And also we want to add the autoscaling of our workers, which is already supported by the main Elm chart. So it's using Keta. But since we're using our homegrown Shopify deployment strategy for Kubernetes, we need to explicitly adopt it or integrate it to our code base. And also something we want to add is the ability for your users from the Airflow UI to be able to search and discover any DAGs across all instances. Because right now, if they're not necessarily aware of their project and whatnot, or the requirement is that the users need to know which project they're looking for before even, so they can be directed to an instance. But if they don't know exactly the project, it's kind of opaque. And something we look forward to is being able also to get back to the other part of our infrastructure, because we also support like the query engine, the batch processing engine like Spark and whatnot. So now that we've given a lot of love to Airflow, we're able to focus on other parts of the system that now need more love. So yeah, next. And we're ready for questions. Thank you. And yeah, is there any questions? Well, I think there will be a session in a few minutes. Sophia, or?
We have a question online. Is Surf available on GitHub?
That was one of the bullet points we had. Unfortunately, no, Surf is not, because it's tightly bound to all the Shopify infrastructure. There is no reason for us not to share that code, other than it's so bespoke that it may not be relevant. So I would say feel free to reach out to me, and we could even have a chat and show you some code snippets. But it is unfortunately not available on GitHub. Sorry. If anything, that's a segue into what Astro is doing. Astronomy, or the company that support Airflow, a lot of the open source contribution, they do have a command line called Astro CLI, I think. It does something quite similar. But yeah. But at the same time, their main offering is a SaaS offering, which honestly, depending on your scale, may make a lot of sense for us. We already had a strong, Airflow culture established at Shopify. It's just that we needed to put the project in a better state infrastructure-wise. And also by the amount of tasks that we're doing per day, the cost would have been quite prohibitive, but yeah. But otherwise, their solution is quite compelling.
Awesome, thank you. Another question, how do we get in the discussion session? Is there a Zoom call? No, it's not a Zoom call. If you type your question in the YouTube chat box, we will be able to see it and answer the questions.
No, I think Bruno is referring to a session at 12:30 my time, PST, and I think it's for an hour where we can just chat about random questions on, yeah.
Gotcha. Thank you for clarifying.